So how do we use this ratio test? We're going to go through a few examples, and then in the next video we'll see more. So let's start with the series from 1 to infinity of -1 to the n multiplied by n cubed over 3 to the n, and we want to know whether this series is convergent or not. So why would we use a ratio test for something like that? Well, typically we use a ratio test for things that involve powers and exponentials. So things like powers of n or powers of a constant that depend on n. So this n cubed and 3 to the n are typical examples. The other class of series that are particularly suited for a use of the ratio test are things that involve the same kind of things and possibly factorials, as we will see in examples 3 and 4. So if we're going to use the ratio test, we look at the absolute value of the quotient of two consecutive terms. So in absolute value, the -1 to the n is going to be dropped, and then the absolute value of an is n cubed over 3 to the n, absolute value of an plus 1, n plus 1 cubed over 3 to the n plus 1. So the first fraction here is an plus 1, the second one is the reciprocal of an. So, because of course, if I divide an plus 1 by an, it's like multiplying an plus 1 by the reciprocal of an. And now, if I look at what I have here, I have 3 to the n divided by 3 to the n plus 1. 3 to the n is really nothing but the product of 3 by itself n times, and 3 to the n plus 1, product of 3 by itself n plus 1 times. So n of these 3's cancel out, and what remains is one of these 3's at the bottom, so we get 1/3. On the other hand, n plus 1 cubed over n cubed is really n plus 1 over n, everything cubed, and n plus 1 over n can be written as 1 plus 1 over n, and we cube that. And now what we're interested in is the limit of this absolute value of the ratio n plus 1 over n. So when n goes to infinity, what's in the parentheses goes to 1, and when we cube it, it goes to 1. So the limit of our ratio is 1/3, which is less than 1. And therefore, by the ratio test, we can conclude that this series is absolutely convergent, and therefore, in particular, convergent. In the second case, we have something that is pretty similar to geometric series of common ratio 2/3. A direct comparison is not that easy. Of course, we could use limit comparison, for instance, and we will see that this works just fine. But in any case, we have powers, and so you might want to use a ratio test. That's at least a possibility. So we look at the ratio of two consecutive terms, an plus 1 over an. So we get 2 to the n plus 1 plus 5 divided by 3 to the n plus 1. And then we multiply by the reciprocal of an. So that's 3 to the n divided by 2 to the n plus 5. Just like before, we have 3 to the n over 3 to the n plus 1. That's 1/3. And then what remains is 2 to the n plus 1 plus 5 divided by 2 to the n plus 5. We can factor out 2 to the n at the top and at the bottom, and then cancel that 2 to the n out. And what we obtain is that in the parentheses, the top goes to 2, the bottom goes to 1, so we have 1/3 multiplied by something going to approaching 2, and therefore the limit is 2/3, which is less than 1, strictly less than 1, and therefore, by the ratio test, we can conclude that this series is convergent. Well, the conclusion of the theorem is that it's absolutely convergent, but here we have a series with positive terms, so it's really just the same thing. Now, as I mentioned, we could use an alternative argument, which here is really essentially the same thing, is to remember that when we looked at the proof of the ratio test, it comes down to comparing the asymptotic behavior with the behavior of a geometric series. And here we could do a direct limit comparison with the geometric series of common ratio 2/3. So the Bn that we use for limit comparison test would be 2/3 to the n. And if we look at an over Bn, then we have 2 to the n plus 5 over 3 to the n, that's my an. And I multiply by the reciprocal of Bn, that's 3 to the n over 2 to the n. The 3 to the n cancels out. We get the limit of 2 to the n plus 5 divided by 2 to the n. This has limit 1, which is a non-zero finite number. And that's what we need in the case of the limit comparison test. Now remember, when we get limit 1, we have a problem for the ratio test, but not for the limit comparison test. And that's what we're looking at here. So here the conclusion of the limit comparison test is that the behavior in terms of convergence of the series of AN is the same as the behavior of the series of BN. And we know that the series of BN is really the series of 2/3 to the n. It's a geometric series of common ratio 2/3. Therefore it is convergent because the common ratio is in absolute value less than 1. So by the limit comparison test, the series of AN is also convergent. That's an alternative way to deal with that one. Now for our third example, we have the series from 1 to infinity of 10 to the n over n factorial. Both top and bottom go to infinity very quickly, but we want to know whether the corresponding series is convergent or not. And because we have powers, like 10 to the n, and factorials, which are really products, then the ratio test is an appropriate tool. So let's see how that works. We look at the quotient of two consecutive terms, an plus 1 over an. An plus 1 is 10 to the n plus 1 divided by n plus 1 factorial. We multiply by the reciprocal of an, which is n factorial divided by 10 to the n. We have 10 to the n plus 1 over 10 to the n. Well, 10 to the n plus 1 is really 10 to the n that I multiply again by 10. So that simplifies as just 10. And then I have n factorial over n plus 1 factorial. If you think of what n factorial is, it's really just a product of the first n consecutive integers, so 1, 2, 3, and so on up to n that I multiply together. N plus 1 factorial is the same thing, except that I don't stop at n, but I add one more factor, n plus 1. So we get something like that, where you see that you can cancel out the product 1, 2, 3 all the way through n, and what remains is n plus 1 at the bottom. So we end up with just 10 over n plus 1. And what we're interested in is the limit of this ratio. So the limit is the limit of 10 over n plus 1, which is of course 0, and that is less than 1. Remember again, in the limit comparison test, when we have limit 0, we cannot conclude. In the ratio test, it's when we have limit 1 that we cannot conclude. A limit of 0 is no problem at all. It is some limit that is less than 1, and therefore we can conclude by the ratio test that this series is convergent. Another example involving factorials is this exercise number 4, where we have the series of general term 2n factorial divided by n factorial multiplied by n factorial. So again, I'm going to look at the quotient of two consecutive terms. When I replace n by n plus 1 in my general term, I get 2n plus 2 factorial divided by n plus 1 factorial squared. Then I multiply that by the reciprocal of an, which is n factorial squared at the top divided by 2n factorial. And then I'm going to see what I can simplify. I have n factorial over n plus 1 factorial. We just have seen how that works, right? N factorial is the product of the first n integers, n plus 1 factorial, the product of the first n plus 1 integers. Everything cancels out except n plus 1 at the bottom, so we get 1 over n plus 1. Then we have that twice, so I get 1 over n plus 1 twice. And then we have 2n plus 2 factorial divided by 2n factorial. 2n plus 2 factorial is again the product of the first 2n plus 2 integers. So it's 1 times 2 times 3 times 4 and so on, all the way up to 2n plus 2. 2n factorial is 1 times 2 times 3 and so on, all the way up to 2n. So you get something like that, where at the top you go all the way to 2n and then multiply by the next integer, which is 2n plus 1, and then the next integer, which is 2n plus 2, which is the last one. At the bottom we stop at 2n. So everything cancels out except 2n plus 1, 2n plus 2 at the top. So we can cancel that out, and we end up with 2n plus 1, 2n plus 2 divided by n plus 1 squared. Now what we have here is a quotient of two polynomials in n. At the top, we have a polynomial of degree 2 with leading coefficient 4. Right? If you multiply things through, the term of highest degree is going to be 4n squared. At the bottom, you have also a polynomial in n of degree 2, but if you multiply things through, the leading term is n squared. So you have something of the form 4n squared plus a bunch of stuff divided by n squared plus a bunch of stuff. You end up with limit 4, which is greater than 1, and therefore by the ratio test we can conclude that this series is divergent. Now turn to the next video where we're going to look into more examples.